So let's consider a simple problem. Okay. The language is strings followed by their reversal. So strings, W, let me put the punctuation character, followed by their reversal. Okay. So for example, 0011 pound 1100. So that's an example of such a string. Okay. And these are like palindromes, except there's a punctuation character here. So can we construct a context-free grammar for this language? Very easy. Okay. So here we go. And I ask you to verify this. So here's a context-free grammar that generates strings in this language. Well, you can either produce the punctuation character, or you produce 0s0, or you produce 1s1. So what's happening? You take your string, think of it as you take your start variable, and you can enclose it in zeros or enclose it in ones. So whatever you put on one end, you put on the other end, so that when you reverse it, it's going to remain the same. Okay, so let's see an example of a derivation. S goes to 0s0, goes to, now I'm going to replace with 1s1, so it goes to s, 1s1, and then 0, and then I'm going to put the pound here. So 0, 1, replace s with pound, and then 1, 0. So look, something, and then it's reversal. So this generates exactly the strings that, correspond to kind of like palindromes with a punctuation. Okay. Now remember I told you that, context-free grammars are essentially like DFAs, but you've added the stack memory. Okay. So let me show you that we can solve this problem with stack memory and a DFA. Okay. So, here's your DFA. It's got its states, which it can roam around. Okay. And let's say we have, our input string 0, 1, pound, 1, 0. Okay. So we have our input string, and it's reading in the input string bit, and we have our stack. Okay. And what the DFA does is it starts off in I'm reading in and pushing onto the stack. So it reads in, it's in a state where it's reading and pushing. So it reads in and it pushes 0 and 1. Okay, so it reads in and pushes 0 and 1. Okay, now the moment it hits the pound, it switches states. Okay, and it says, okay, I'm no longer reading and pushing. Now for every bit that I see, I need to compare with what's on the top of the stack and remove what's on the top of the stack. Why? Because now the next bit should match this. The next bit should match that. Okay, so this should match what's on the top of the stack, and then if I remove that, the next bit should match what remains on the stack, and so on. Okay? So I move into the comparing phase, where now I read this 1 and I compare, match, and remove. I read this 0, compare, it matches, I remove. Okay, and when I'm done with the bits, I check if the stack is empty. The stack is empty, so I'm ready to accept. If anything goes wrong in this process, I reject. So there, a DFA with stack memory can also solve this problem. And that's starting to look kind of suspicious. Yeah, wow, okay, so what you can generate with context-free grammars those problems can be solved by DFAs. It turns out that that's more or less correct. DFAs with stack memory are more or less equivalent to context-free grammars, except for one small tweak. Okay, so I'm going to ask you to give a context-free grammar for this same language without punctuation. So L equals W, W reversal. I'll give you 5 seconds. It's not so hard to do given this. Okay. So 1, 2, 3, 4, 5. Now, if you're coming back just to see how we solve that, how we generate strings from this language using a context-free grammar, it's basically the same context-free grammar, except I don't put a punctuation, I put the empty string. So S goes to empty, or 0s0, or 1s1. There. Okay. Now you can try to figure out if you can create a DFA with stack memory that solves that problem. It turns out you cannot. Okay. And what's the basic idea? The basic idea is when the DFA is roaming around and reading in bits, okay, it's pushing. Now when it read the punctuation, that tells the DFA stop pushing and start comparing. Start popping and comparing. The problem when you don't have the punctuation is it doesn't know when to stop pushing and when to start comparing. Okay? And the punctuation is very helpful for that. Even though these are more or less the same language, okay, the punctuation helps the DFA with a stack. Now it turns out that you can add a little bit more capability to this DFA and make it what's called non-deterministic, and then boom, it can solve that problem. And then indeed, non-deterministic DFA with a stack, or what are called non-deterministic pushdown automata, are equal in all aspects to context-free grammars. Okay, but we won't get into that detail. It's not a big deal for us to have punctuation. Okay, so conclusion. CFG are basically, equivalent to DFA plus stack. Okay. Okay. Now let's make another twist. What about if it was not the language LW pound W, but LW pound WR reversal? Instead, I'm going to change it to LW pound W. Okay, so L equals W pound W. So repetition. So now I still have the punctuation to help the DFA, but it's not reversal, it's repetition. So let's see what happens when the DFA with stack tries to solve that problem. Okay, so let's pick an example. So let's say 0, 0, 1, pound 0, 0, 1. So my DFA is operating. Okay, and what it's doing in the initial phase is it's pushing onto the stack until it sees the pound. So it's pushing. It pushes 0, it pushes 0, it pushes 1. So it starts here, pushes 0, 0, 1. Now it hits pound. It says, okay, now I should start comparing. So it hits 0. Okay, and now it goes to the stack, but there's a problem. What's the problem? I give you a few seconds. 1, 2, 3, 4, 5. Okay. The problem you should have noticed is that it needs to compare this 0 not with what's on the top of the stack, but it needs to compare this 0 with what's on the bottom of the stack. But a stack doesn't give you access to the bottom. A stack is top access only. Okay, and so that's the basic deficiency of this current computing model, a DFA with stack memory. Cannot solve this problem. Okay, and it turns out that there's no CFG that can generate that either. Okay, no surprise, because these guys are basically the same. It turns out that there are other problems for which you cannot solve with a stack for exactly the same reason, that you only have access to the top of the stack, but what we would like is access to the bottom or maybe somewhere else in the stack. What we would like is random access to the stack. Okay. Now, here are some other problems that are, not able to be generated by CFGs or be solved by DFAs with stacks. What are those problems? Here, another example. L equals, a triple equality. 0 to the n, 1 to the n, 0 to the n. So equals, equals, equals. Triple equality. So triple equality. Okay, squaring. L equals 0 to the n, 1 to the n squared. So this is square. Why do I say squaring? Because you have a number of zeros and the square of that in terms of ones. So the number of ones is the square of the number of zeros. What about exponentiation? 0 to the n, 1 to the 2 to the n. So exponent. So the number of ones is 2 raised to the power of the number of zeros. So you can think of that as exponentiation. These are, we want to be able to solve these problems. Okay. CFG cannot generate those languages and DFA cannot solve those problems. Okay. So we need something more. Okay. So where are we at? We've explored DFA, we've explored CFG. Okay, CFG is DFA with stack, and they're very powerful, but and DFA alone without stack can't solve equality. DFA with stack can't solve some other important problems like repetition, triple equality, squaring, exponential, and many, many other problems cannot be solved. Okay. So we need something more. And what's the fundamental deficiency? The fundamental deficiency here is top access only memory. Okay. And we thought that should be enough, but can't solve basic things. So what maybe we need is a random access memory. Okay. And voila! A DFA not with stack memory, which is top access only, but a DFA with random access memory, okay, is going to be what we're going to talk about next. And it turns out that is going to be super powerful, and we're going to show that. Okay, so DFA plus random access memory is actually going to be our model of a computer, and it's going to be very powerful. And that model, DFA plus random access memory, is called a Turing machine. So we're going to get to Turing machines next. Okay. For now, checking out.